To determine the locked rotor current, or LRA, when you know the kVA code, follow these steps. Firstly, determine the kVA rating. The kVA code is a two-component code such as 4-3 or 10-1.15. The first number indicates the rated kVA and the second number indicates the locked rotor kVA or kVA. For example, for a kVA code of 4-3, the rated kVA is 4 kVA and the kVA is 3 kVA. Secondly, calculate the locked rotor current or LRA. Use the following formula: LRA equals kVA times 1000 divided by voltage times 1.732, where LRA is the locked rotor current in amps, kVA is the locked rotor kVA from the kVA code, voltage is the motor's nameplate voltage in volts, and 1.732 is a conversion factor from 3-phase kVA to 3-phase amps. For example, if the voltage is 230 volts and kVA is 3 kVA, then LRA equals 3 times 1000 divided by 230 times 1.732, which is approximately 6.8 amps. Therefore, the locked rotor current for a motor with a kVA code of 4-3 is approximately 6.8 amps. It is important to understand each component of the formula to accurately calculate the locked rotor amps. Firstly, the kVA represents the motor's inrush kVA when the rotor is locked, or stationary, at startup. Secondly, the voltage refers to the motor's rated voltage, typically found in the motor's nameplate. Using the correct voltage value is crucial for accurate LRA calculation. Thirdly, the constant 1.732 represents the square root of 3, which is used for 3-phase power calculations. This constant accounts for the phase difference in a 3-phase system. By understanding these elements and correctly applying the formula, you can effectively determine the locked rotor current from the kVA code. In practical applications, the locked rotor current is an essential parameter for selecting appropriate circuit protection devices such as circuit breakers or fuses, and for ensuring the motor's starting characteristics align with the electrical system's capabilities. The kVA code provided on the motor nameplate offers valuable information for electrical engineers and technicians involved in motor selection, installation, and protection. Now let's delve into some additional insights and considerations regarding locked rotor current and kVA codes. Understanding the significance of LRA in motor applications. Firstly, locked rotor current, also known as inrush current, is the maximum current drawn by a motor when it is initially energized but its rotor is not yet rotating. This current can be significantly higher, typically 6 to 8 times the motor's full load current. Secondly, LRA is a critical factor in determining the appropriate size of circuit protection devices, such as fuses or circuit breakers, to prevent nuisance tripping during motor startup. Thirdly, understanding LRA is crucial for assessing the impact of motor starting on the electrical distribution system, ensuring that voltage drops remain within acceptable limits. Exploring the kVA code and its components. Firstly, the kVA code, as found on the motor nameplate, provides a standardized way to represent the motor's locked rotor kVA per horsepower. Secondly, the kVA code consists of a letter ranging from A to V, each corresponding to a specific range of locked rotor kVA per horsepower. Thirdly, a higher letter indicates a higher locked rotor kVA per horsepower, which translates to a higher inrush current during motor starting. Deciphering the kVA code table. Firstly, manufacturers provide tables that correlate the kVA code letters to the corresponding kVA per horsepower values. Secondly, by consulting this table, you can determine the motor's locked rotor kVA per horsepower based on its kVA code. Thirdly, this information, along with the motor's horsepower rating, allows you to calculate the total locked rotor kVA and subsequently the LRA. Utilizing the LRA for practical applications. Firstly, the calculated LRA is used to select appropriately sized circuit protection devices, ensuring that they can withstand the inrush current without tripping. Secondly, the LRA value is also used to assess the voltage drop during motor starting, ensuring that it remains within acceptable limits as per standards like the National Electrical Code, or NEC. Thirdly, if the voltage drop is excessive, measures such as using reduced voltage starters or increasing the size of the supply conductors may be necessary. Factors influencing the LRA: firstly, the motor's design, including the number of poles and winding configuration, affects its LRA. Secondly, motors with higher horsepower ratings tend to have higher LRA. Thirdly, the supply voltage can also influence the LRA, with lower voltages generally resulting in higher currents. Considerations for motor starting methods: firstly, across-the-line starting, where the motor is directly connected to the power supply, results in the highest LRA. Secondly, reduced voltage starting methods, such as auto-transformer starters or part-winding starters, can significantly reduce the LRA. Thirdly, the choice of starting method depends on the application, the electrical system's capacity, and the permissible voltage drop. Now let's explore how to apply this knowledge in practical scenarios and address common challenges. Calculating the LRA for different motor types. Firstly, for three-phase induction motors, the formula LRA equals LR kVA times 1000 divided by voltage times 1.732 is commonly used. Secondly, for single-phase motors, a similar formula can be used, but the constant 1.732 is replaced with 1, reflecting the single-phase nature of the supply. Thirdly, for specialized motors, such as synchronous motors, the LRA calculation may require additional considerations based on the motor's specific design and operating characteristics. Addressing voltage drop concerns. Firstly, excessive voltage drop during motor starting can cause other equipment on the same circuit to malfunction or experience reduced performance. Secondly, to mitigate voltage drop, consider using larger supply conductors, reduced voltage starters, or dedicated circuits for motors with high LRA. Thirdly, conduct voltage drop calculations to ensure compliance with standards like the NEC, which provides guidelines for acceptable voltage drop limits. Selecting appropriate circuit protection devices. Firstly, fuses and circuit breakers are designed to protect motors and electrical systems from overcurrents, including those caused by high LRA. Secondly, the selected circuit protection device must be able to withstand the motor's LRA for a short duration without tripping, while still providing adequate protection against sustained overloads or short circuits. Thirdly, refer to the NEC and manufacturer's recommendations for proper selection of circuit protection devices based on the motor's LRA and full load current. Troubleshooting motor starting issues. Firstly, if a motor fails to start or trips its circuit breaker repeatedly, a high LRA may be the cause. Secondly, check the motor's nameplate data, the supply voltage, and the condition of the motor and its starting components. Thirdly, consider using a motor starting analyzer to measure the LRA and diagnose any issues with the motor or its starting circuit. Implementing energy-efficient motor starting strategies. Firstly, reduced voltage starters not only reduce the LRA, but also contribute to energy savings by minimizing the inrush current and associated losses. Secondly, variable frequency drives, or VFDs, offer advanced motor control capabilities, including soft starting, which further reduces the LRA and improves energy efficiency. Thirdly, consider implementing energy-efficient motor starting strategies to reduce energy consumption and improve the overall performance of electrical systems. Now, let's expand on these concepts to cover advanced topics and real-world applications. Advanced techniques for LRA calculation. Firstly, for complex motor applications, advanced simulation software can be used to model the motor's behavior during starting and accurately predict the LRA. Secondly, these simulations can take into account factors such as the motor's load, the supply impedance, and the characteristics of the starting circuit. Thirdly, advanced LRA calculation techniques provide a more comprehensive understanding of motor starting dynamics and enable optimized system design. Integrating LRA considerations into the electrical system design. Firstly, when designing electrical systems, it's crucial to consider the cumulative effect of multiple motors starting simultaneously. Secondly, the system must be able to handle the combined LRA of all motors without experiencing excessive voltage drop or overloading the supply transformers. Thirdly, proper coordination of circuit protection devices is essential to ensure that the system can selectively clear faults without disrupting the operation of other equipment. LRA and motor control centers. Firstly, motor control centers, or MCCs, are commonly used to house and control multiple motors in industrial facilities. Secondly, MCC incorporates circuit breakers, starters, and other control components designed to handle the high LRA associated with motor starting. Thirdly, the design and layout of MCC must consider the LRA of each motor to ensure reliable and safe operation. Standards and regulations related to LRA. Firstly, the NEC provides guidelines for motor circuit protection, including requirements for selecting circuit breakers and fuses based on the motor's LRA and full load current. Secondly, other standards, such as those published by the Institute of Electrical and Electronics Engineers, or IEE, offer recommendations for motor starting methods and voltage drop limits. Thirdly, compliance with these standards and regulations is essential to ensure the safety and reliability of electrical systems. Case studies of LRA-related issues. Firstly, in industrial facilities, improperly sized circuit breakers or inadequate supply conductors can lead to nuisance tripping and equipment downtime due to high LRA. Secondly, by analyzing the LRA and implementing appropriate mitigation measures, these issues can be resolved, and system reliability can be improved. Thirdly, case studies provide valuable insights into the practical challenges associated with LRA and offer guidance for effective solutions. The role of LRA in renewable energy systems. Firstly, in renewable energy systems, such as wind farms and solar power plants, motors are used to drive pumps, fans, and other equipment. Secondly, understanding the LRA of these motors is crucial for designing stable and reliable power systems. Thirdly, special considerations may be necessary to address the impact of intermittent renewable energy sources on motor starting performance. Now, let's explore the latest advancements and future trends related to locked rotor current. Advancements in motor starting technologies. Firstly, solid-state starters and soft starters offer precise control over motor voltage and current during starting, significantly reducing the LRA and improving motor performance. Secondly, these technologies also provide advanced protection features and communication capabilities. Thirdly, advancements in motor starting technologies continue to drive improvements in energy efficiency and system reliability. The impact of smart grids on LRA management. Firstly, smart grids enable advanced monitoring and control of electrical systems, providing real-time data on motor performance and LRA. Secondly, this information can be used to optimize motor starting strategies and prevent voltage drops or overloads. Thirdly, smart grid technologies are transforming the way we manage and control motor starting in modern power systems. Future trends in LRA research. Firstly, ongoing research is focused on developing new motor designs and control strategies that further reduce the LRA and improve motor efficiency. Secondly, these efforts include exploring advanced materials, innovative winding configurations, and intelligent control algorithms. Thirdly, future trends in LRA research hold the promise of more efficient and reliable motor systems. I hope this information has provided you with a deeper understanding of locked rotor current kVA codes and their significance in electrical systems. Remember, accurate LRA calculation and proper consideration of motor starting characteristics are essential for ensuring the safety, reliability, and efficiency of electrical installations. Stay curious, keep learning, and continue to explore the fascinating world of electrical engineering.